Okay, so we discussed these two different perspectives of LQG, the CFT perspective on the one hand, and the random surfaces perspective. And now, in the next part of the talk, I'm going to discuss the kind of exact formulas that you can get from these two perspectives, starting with Liouville CFT. Okay, so the first result I want to mention is a celebrated breakthrough of Anti-Remiros and Franz Vargas. So we call this 3-point function for the sphere. You add 3 insertions at 3 points on your Riemann sphere. You define this Liouville field with these insertions, and you take the expected value of e to the minus the quantum area. And again, this is just going to become some kind of GMC. So it's nothing too fancy. So the miracle is that you can get an exact formula for this quantity called the DOZZ formula. And the exact formula is written here. So as is the case with CFTs, because of conformal invariance, the locations of your 3 points don't really matter too much, right? Because 3 points in the sphere are exactly the right number to fix the conformal structure. For any 3 points and any other 3 points, you can take the conformal map from one triple to the other triple. And so the fact that the dependence on the z is trivial is pretty easy. The non-trivial thing about this correlation function, though, is the DOZZ formula, this prefactor. And the result that is, the formula is given by this expression over here. So, as usual, it involves these double epsilon functions, which are defined by these integrals. So, okay. So, this formula was a little bit contentious in physics, as Antti could probably tell you. But so having a mathematical proof, is very important. Okay. So I'll say a bit about this exact formula here. It's defined in terms of this double epsilon function, for which we gave this integral expression on Tuesday. And I realized after the talk, maybe this is maybe the most compact way of presenting this formula, but maybe not the most insightful. So the reason why this shows up is because it satisfies these shift equations. So when you perturb the parameter by either b or b inverse, the ratio that you get is going to be explicit and fairly simple if you think gamma functions are simple. Okay, so on the one hand you have this integral, but on the other hand, these are really the reason why these formulas show up. And the proof of the DOZZ formula that Antti and co-authors gave was by proving that it satisfies these shift equations, which are related to these ones. And so once you can write down equations of this form for the 3-point correlation function, then you can express it in terms of these double epsilon functions of Zamolodchikov. Okay, I'm not going to go into too much detail here. I'll just mention that the key input to proving these shift equations for the 3-point function, these come from the BPZ equations in CFT. Okay, so this massive Liouville program, right? So first they constructed probabilistically using the Gaussian free field, the correlation functions. Then they solved for the 3-point correlation functions shown here. And then finally they solved for all the higher order correlation functions, completing the theory rigorously. So I'm going to say a bit about this last step. So there are 2 different approaches that you can take when you study conformal field theory. The first approach is the one that I gave on Tuesday, this naive definition where you actually have a random field, and then you take measurements of this field and take expected values and use that to define correlation functions. Right? So that's the path that we've been following using the Gaussian free field. On the other hand, there's a more algebraic method where using representation theoretic arguments, this breakthrough paper of Berlyavin, Polyakov, and Zermologikov gave some kind of recurrence relation that should hold for every CFT, not just Liouville, any 2D CFT, where you can express higher order correlation functions, like 4 points, 5 points, 6 points on the sphere, in terms of lower order correlation functions. So it's like solving a system of equations. And if you can write down formulas for the most fundamental correlation functions, which are your 3-point sphere functions, then you can write down all of your correlation functions. Now the problem with the second approach is that it's not, it depends on these symmetries. It doesn't actually tell you that you get a CFT. So this system of equations that you get is overdetermined. There are multiple ways of expressing the same 4-point function in terms of 3-point functions. And then you have to ask, do these two expressions agree? So, does the conformal bootstrap give you a consistent theory of these values of the correlation functions you get? Do they satisfy all of these overdetermined system of equations? So the breakthrough work of Antti and Rose and Vargas is that these two approaches indeed agree in the case of Liouville theory. Okay, so if you care about computing every single correlation function, you can start with the 3-point correlation functions that they already derived, and then combine them in some way to get 4-point functions, 5-point functions, and so on and so forth. So, as I mentioned on Tuesday, the goal in CFT is to compute every correlation function. So this third step in their landmark program, completes this for the case of Liouville. Okay. Are there any questions about this? Okay. It's worth emphasizing that for Liouville, this program was carried out by these authors for the case of surfaces without boundaries, so closed surfaces. If you instead care about surfaces like the disk, you have more structure constants, not just 3 points on the sphere. You get 3 points on the boundary of a disk and a one bulk, one boundary correlator. And then these results are also known now. But the boundary conformal bootstrap, which expresses higher order boundary correlation functions in terms of these two functions, this is, as far as I understand, work in progress. Okay, so that's the kind of solvability that you get in the Liouville CFT perspective. In short, just all of your correlation functions for closed surfaces are known, and for surfaces with boundary, you can handle the disk at least. Okay. So that's one perspective. The other perspective is in terms of random surfaces. And here, it turns out that when you have gamma Liouville quantum gravity and kappa SLE or CLE, conformal loop ensemble, you get these solvability kinds of statements as well. And one source of these is coming from the discrete world, from random planar maps. So I mentioned that near the start of this series of talks that convergence of random planar maps to LQG is very difficult, but weaker notions of convergence, weaker than the conformal embedding and the measures converging, these weaker notions are known in some cases. So one example is an FK decorated random planar map. So you have a random planar map model weighted by the partition function of the FK random cluster model, and that's going to give you a collection of loops on the surface. And this is known to converge to LQG with CLE in a certain topology. I'm not going to go into details for this first one because we're not going to use it. The second one we will use, and it states that ON loop model decorated random planar maps converge to LQG with CLE, and the topology of convergence that is used is that the length of the loops have the correct scaling limit, which is the length of the loops of CLE on LQG. Okay, so you take a disk random planar map weighted by the ON loop model partition function, you sample an ON model, you look at the outermost loops. There's finitely many of them. You look at the lengths, and then you just take a scaling limit of these lengths as the number of faces of your map tends to infinity, and that converges to the lengths of the loops in Liouville quantum gravity, decorated by independent conformal loop ensemble. Okay.
Yeah. So what are the particular values of gamma and kappa in these cases?
Yeah. So, okay. So there's it's a function of n. So you actually get a pretty wide range. It'd be difficult for me to write the exact relationship right now, but you end up with gamma between, let's see, probably something like this. And kappa is gamma squared, or gamma between root 2 and 2. And kappa is 16 over gamma squared. And then these correspond to certain n values, which I'm not going to attempt to write down. Yeah. So you get a continuum of values. So unlike the discrete models I discussed at the start of today's lecture, where we just have 8/3 or root 2 or 8 or something, you get all the values in these intervals. Are there any other questions? Okay. So the kind of solvability result you get from this ON loop model is the following. So here's a story. It's the same story I drew before at the end of the last lecture. You have one of these LQG disks, and on top of it you draw an independent conformal loop ensemble, and you just look at the outermost loops. I've drawn those in red here. There should be countably many of them, but I just drew like 5 or something. So each of these loops has a certain random length, which is measured with respect to the Gaussian free field. So it's like the exponential of the Gaussian free field integrated along the loop. And I'm going to call these lengths L1, L2, ... in decreasing order. So there's finitely many loops which have size larger than 0.1, but infinitely many loops in total, because you have lots of small loops. Okay, so on the one hand, you have this very complicated object, LQG with CLE, and then you measure a bunch of loops. On the other hand, you have this simple object. This is some kind of a sketch of a Liouville process, more specifically a stable Liouville process with the index given by 4 over kappa plus 1/2. So this is a process which only has upward jumps, which are shown here in red, and as somehow it still manages to go down because fractals. But you run this process starting at time 0, at space 0, and you stop the moment it hits the value -1. And then you do some kind of weighting in terms of how long it took you to hit -1. Okay, so you have a Liouville process, you weight it by some natural observable, and then you look at the collection of all of the jump sizes that you get in this picture. And let's call these jump sizes x1, x2, ... in decreasing order. And the theorem is that these two observables agree exactly. The complicated observable, which is the joint law of all of your loop lengths, this agrees with the collection, agrees in law with the collection of all jump sizes. Okay. So, yeah.
So, the number of jumps are finite, or
the number of jumps is infinite as well.
So it's infinite. It's infinite small jumps, you mean?
Yeah, exactly. So if at the scale you only see like 10 jumps, but you zoom in at any of these portions, there's infinitely many jumps. Yeah. Are there any other questions? Okay. So this statement, we don't know how to prove it directly in the continuum. The only argument I know goes through the discrete. So, okay. There are 3 inputs. The first is the result of Miller, Sheffield, and Werner, where they kind of start with one of these LQG disks and they explore it by some curve. At various points in time, the region they're exploring gets cut into 2 regions and it fragments. At other times, this exploration hits a CLE loop, and then the boundary length of the unexplored region jumps up, etc. They define some kind of stochastic process called a growth fragmentation process, from which you can produce these ln lengths. Okay, so this first paper is directly in the continuum. You define the stochastic process, and then it gives you these loops, these lengths. The second is a scaling limit result, which says that if you start with these random planar maps decorated by ON loops, then the loop lengths in the discrete converge to these LNs that you get from the growth fragmentation process. The third result gives you a different continuum description of the LNs, not using a growth fragmentation process, but using these jumps of the Liouville process. Sorry. Yeah. So combining these three results tells you that the LNs agree in all of the accents. And something very non-trivial is going on in this argument, because the way that this last paper is done is via some kind of discrete bijection, some kind of argument you can only carry in the discrete, which some kind of operation you apply to a tree, which you cannot do in the continuum. So it'd be an interesting question whether you can directly prove this theorem without passing through this discrete argument. Okay. So that's the kind of solvability result that we get for gamma LKG with CLE. And as a consequence of the solvability, you get a statement along the following lines. I didn't define a quantum annulus, so I should just draw a picture now. Let me just draw a picture. I can switch it on. Yeah, thank you. So, what we spoke about before the break is if you take a quantum disk and cut by CLE, you get conditionally independent quantum disks. This is a somewhat smaller version, a somewhat simpler version of that statement, where you only look at one loop. So, so on the left-hand side, you have a quantum disk with one marked bulk point. You sample an independent conformal loop ensemble on top of it. I just keep this outermost loop around the marked point. Now you cut along this loop, what you're going to get is a pair of surfaces, one of which has the annulus topology, and the other of which has a disk topology. And the statement is that this object, we'll call it a quantum annulus. And QAA, comma B is going to denote the quantum annulus with boundary length equal to outer boundary length equal to A and inner boundary length equal to B. I should specify this one has a boundary length of A. This disk has a boundary length of B. And then you integrate over all choices of B. And again, because there's different ways that you can glue the disk to the annulus, you have this extra factor of B here. So as a direct corollary of this result that we mentioned before the break, if you take a quantum disk with one marked point and you cut by a CLE loop, you get two pieces which are conditionally independent given the length B of the loop.
So the annulus, do you define it by each result, or you define it independently?
Can you repeat the question? What's the question again?
How do you define the quantum annulus?
Oh, you define it this way.
Okay.
Yeah. Yeah. So QAAB is defined to be the measure such that this holds. Yeah. we know such a measure exists from this Miller-Sheffield-Werner result. Yeah. Are there other questions? Okay. Let's go back to the slides then. It turns out that the solvability of the length of CLE on LQG gives you some kind of solvability for the quantum annulus. Yeah. Sorry, can we get the slides on, please?
I think you just need. I think you have the control there.
Oh, I have no. I thought there's someone who like controls the thing.
Yeah. I think there is. There's just slow.
So we wait, I guess, or I can write the statement down. I think I heard it. Okay, good. Okay, so with this definition of the measure QA for the quantum annulus, you can exactly deduce the partition function of quantum annulus having boundary lengths A and B respectively. Okay, and it turns out that it's going to be given by this formula. We've got some constant we don't care too much about. And then you have this 1 over square AB times A plus B. So how do we prove this? We know that if we take the LQG disk and you cut by every single outermost CLE loop, then you're going to get conditionally independent quantum disks. And if you remove one of these disks, then what's remaining is a quantum annulus. And so, since we know the lengths of all of these, the law of the length of all of these loops, you can deduce the law of the length when you remove one distinguished loop, namely the loop surrounding the origin. And I don't go into detail on this point, but from this exact formula in terms of Liouville processes, and from the definition of the quantum annulus by cutting by a single loop, you can deduce the partition function of the quantum annulus. Yeah.
So the loop you remove, but then sorry.
Yeah.
So there is some size biasing?
Exactly, that's right. Yeah, the origin is a quantum, it's a point sample from the LQG area measure. So yeah, you have to bias, so you're removing one of these jumps, which is biased by the square of the jump size, because area is length squared. Yeah. Yeah. So you know, this formula comes from some kind of Liouville process computation. Yeah. Other questions? Okay. So you can further, so knowing the partition function of the length A and B is like knowing the joint law of the two boundary lengths of your quantum annulus. So the previous slide tells us the joint law of the lengths. We can further get even finer information. We can get a joint law of both lengths and the area enclosed by the annulus. And this is in terms of the Laplace transform, the daily expected value of E to minus mu times area. And so this quantity describes the law of the area. So the story is essentially the same. You start by cutting an LQG by CLE, and you remove one of the loops. And then the area of the remaining annulus is a sum of the areas inside the loops. Because the CLE itself, it's a fractal with fractal dimension small, so it's not containing any LQG area. All the area of the annulus is contained inside the loops. So you just need to sum that up. And then there's some kind of Liouville process computation you do, and you can just get it somehow. I don't want to go into detail on this point, but directly from the Liouville process description, you can deduce the law of the area. Okay, so to summarize what we've just spoken about, on the Liouville CFT side, the correlation functions are solvable, and all of them have been solved for closed surfaces. Some of them are solved for surfaces with boundary. And these correlation functions describe the joint laws of areas and lengths of random surfaces that we care about, like the quantum disk. On the random surface side, you have these couplings with SLE, and you might be able to get exact formulas for LQG decorated by SLE. And finally, I want to combine these two perspectives to deduce some CLE results. So the first result I want to prove is I want to compute the law of the conformal radius of the outermost loop around the origin of a CLE. So on the right-hand side, I've drawn a nested CLE configuration, and I've drawn in red the outermost loop around the origin. So you can define this notion of distance called the conformal radius. It measures how far the red loop is from the origin in some way that transforms nicely on the conformal map. So the definition is simply, you take any conformal map F, it says psi, I should say F. F from the unit disk with the origin as marked point, into the loop with the origin also as marked point. And you look at the absolute value of the derivative at 0. So the smaller your red loop is on the right-hand side, the more this map F is going to have to shrink things. So F prime of 0 is smaller and smaller the closer your loop gets to the point. So this is some kind of notion of distance from the marked point to the loop. So one of the so there's a theorem of Schramm, Sheffield, and Wilson which computes precisely the law of this random conformal radius of the outermost loop. And it's done in terms of giving this moment of the conformal radius. You get this formula. The way that this result was proved in 2009 was via Edo calculus. And for the next 20 minutes maybe, I'm going to give an alternative, more complicated, less useful, it generalizes better to other topologies, but it's more complicated than what they did. Okay, so are there any questions about the statement before I disappear it? Okay. So let's, thank you. Let's see if I can write this down. Okay, so we're going to draw the same picture I just erased. Okay, on the left-hand side, I have a one-point quantum disk together with an outermost CLE loop. I'm going to call the random field psi. So because of this equivalence between the random surfaces that Sheffield introduced and the Liouville CFT approach, we know that this random field psi can be described as the Liouville field with a single insertion at the origin of size gamma. So we have a gamma size insertion at the origin, and we have a loop around the origin. Now, what I want to do is to cut along the loop and get two different pieces. I also introduce this subscript notation here, where I attach this length A to the notation. So this is a Liouville field restricted to the event that it has boundary length A. It's a probability 0 thing, but you can make sense of this somehow. And yeah, so this is Liouville field with boundary length A with an insertion at the origin of size gamma. Okay. Okay, so the result that I wrote down earlier by which defines QA says, well, we start with the Liouville field with one insertion at the origin and an independent loop. You cut along the loop. That gives you this random surface, which is a quantum annulus. It gives you a disk topology random surface, which is a one-point quantum disk. And again, by this equivalence, the one-point quantum disk is described by the Liouville field with a gamma insertion at the origin. Okay. So now let's do a computation. So the key idea in this argument is we're going to change this insertion at the origin from being size alpha, gamma into being size alpha. The mechanism for doing that, I will now write down. Okay, suppose I start with a Liouville field with insertion gamma at the origin, and I weight its law by e to the alpha minus gamma times the field value at 0 with this epsilon regularization parameter, and I further weight by epsilon to this power. Then as epsilon tends to 0, I'm going to get a Liouville field with a different insertion of size alpha at the origin. Okay, so starting with a gamma insertion, I can get an alpha insertion by weighting by the value of the field at near 0.
At the moment, alpha is something arbitrary, not something statistical.
Yes. So alpha is just arbitrary. Yeah. I'm not going to prove this statement, I'll just write down why we think it's true. So we call the definition of the Liouville field with an alpha insertion at the origin. Well, it's simply going to be the unmarked Liouville field weighted by alpha times the field value at the origin with this regularization and renormalization. We can write down the same formula where you just have gammas of alpha. You just get epsilon to the gamma over 2. You get e to the gamma phi epsilon 0, and everything else is the same. And you just compare these two and like divide one by the other or something. So this, the regularization, this renormalization alpha squared over 2 gets divided by this one. Then this weighting by alpha becomes the weighting by alpha minus gamma. This should be fairly convincing. And I'll put a square box, even though it didn't really do anything. Are there any questions about this claim? Okay. So what we're going to do now is use this little device here to change the picture. Let's see. We're going to weight by exactly that factor. Okay. And then we're going to send epsilon to 0. So what do we get? Well, this weighting doesn't affect these other pieces, it just affects the Liouville field. And the way that we stated it, it just changes the gamma into alpha. Good. So this part of the argument is easier. The harder part is, what happens when we weight this thing by the same quantity. So we immediately run into the problem that on the left-hand side, what is phi? Our field is psi. How do we relate these things? So let's do that now. Okay, so to relate the fields phi and psi, we draw this conformal map F, sending the unit disk with the marked point at origin to the inside of the loop with marked point at the origin as well. So, because these two domain field pairs, where the domain is an interior of the loop and the field is psi, and the domain is the disk and the field is phi, these describe the same quantum surface, the same random geometry. And so the coordinate change formula for Liouville quantum gravity, this definition of random surface, tells us that we need the following identification. Okay, so this is where the random surface perspective really helps us. The field phi is precisely given by, first you map by F inside the loop, and then you look at the value of the field psi, you have this compensation term. Okay. So we want to weight by the value of the field phi in a small circle of radius epsilon here. We draw the circle big so you can see it, but pretend it's really small. So conformal maps change small circles into small circles, roughly. So when you map, you should get a small circle here. And let's call this radius epsilon 1. And the relationship between epsilon and epsilon 1 is epsilon 1 is a shrunk version of epsilon, where you're shrinking by this derivative of f. Okay? So epsilon 1 is just epsilon times f prime at 0. So what is the value of the circle average of phi on the epsilon radius circle? Well, that's the same as the average value of psi on the smaller circle, plus the term you get from this thing, which is going to be q log f prime of 0. Okay, so we know how to relate phi and psi So we can relate the circle average of phi to the circle average of psi. This approximation becomes an equality when you send epsilon to 0. This was not it. Let's take a new talk. Okay, good. So we're going to write this re-weighting factor now. It was epsilon to the alpha squared minus gamma squared over 2 times e to the alpha minus gamma phi epsilon of 0. So this first term we're going to rewrite it in terms of epsilon 1. So it's going to be epsilon 1 over f prime 0, the same power. The second term, we're going to use this substitution. Okay. And now we simply just collect all the terms together. So first you've got this epsilon 1 term together with the field weighting. Okay. And then the rest of it is going to be some power of this f prime stuff. What exactly do we get? Okay. So we weighted the right-hand side of that equation by epsilon to some power times e to something in terms of phi epsilon, and we got a Liouville field with a different insertion. Now we can rewrite this thing. It's exactly the same expression with psi instead of phi, and then you incur this term over here. But remember, the size of f prime at 0 is precisely the conformal radius. So what do we get here? We get some weighted expression. Again, your gamma becomes alpha, right? Coming from this first bit. Then you get this conformal radius weighting. To this power. Okay. So the conclusion is if you take a Liouville field with an alpha insertion at the origin, and you cut by this weighted CLE loop where you have to weight by this conformal radius power, then that's going to give you two surfaces described by the quantum annulus and by the Liouville field with an insertion of size alpha. Okay, are there any questions about this? Okay, this is in some sense the heart of the proof. The rest of it is not too bad. We just write down some observable and conclude. So over here, we have an equality of measures on the left and right hand side. On the left hand side, you have a measure which is a field and a loop. And then when you cut, that gives you a measure describing two different surfaces. But they're the same measure, so they have the same total mass. So we just measure the size of each of the left hand side and the right hand side. So this is what you get when you take the size of the measures on the left and right-hand side. On the left, we have the total size of the Liouville field measure when you have boundary length A and insertion alpha. The total size of this weighted measure, CLE, is a probability measure. When you weight by this conformal radius, the total size of this measure is just the expected, this conformal radius moment. On your right-hand side, you have this integral. You have the size of QAB. It's going to be something like this. And this is coming from the random planar map input. And then you have the size of the Liouville field measure with boundary length B and insertion alpha. Okay, so going from this step to this step, we're just taking the total size. And finally, this is going to be some constant times a to some power. As we discussed earlier, the Liouville field boundary length measure is a power law. So the size of this measure when you have boundary length A is the power of A times some constant. You get the same constant on the right-hand side, so it'll cancel out. And then you're done, if you're very good at integration, I mean. Right? This is a quantity that you want to compute, which is a conformal radius moment. And I have it in terms of some kind of integral of a single variable, some kind of rational function of b, and you just integrate. This is the part where you open Mathematica, type it in, and you play that it gives you something. Okay, so I should say something about constants at this point. These constants k and k prime, these two constants k cancel, so you don't need to know their value. These two don't cancel, you just get some kind of overall constant at the end, but this doesn't depend on the choice of alpha. So you get something like a some kind of function of alpha, and then you get some kind of constant that doesn't depend on alpha. And then you simply plug in the value alpha is equal to gamma. This exponent becomes 0. And so then that lets you compute the constant. So this is fine as well. Okay. Are there any questions about this?
Yeah. Can you repeat how you get this term square root of AB times A plus B?
Yeah, that's a good question. So this is coming from this integrability of LQG declared by CLE. This is a partition function of the quantum annulus. So because you know the loop lengths of LQG plus CLE, you can deduce the partition function of the quantum annulus, which is the region outside one of the loops. And then the formula is just exactly this thing. Yeah. So this is the part where you have the planar map input. Are there any other questions? Okay.
Can you get from this quantum story some Euclidean story? Like for example, for the length of the loops?
Yeah, that one we don't know how to do. It'd be very interesting if you can get the Minkowski content of the loop using something like this. We don't know how to do that. Yeah. Cool. So in the last 5 minutes, I want to return to the slides. Okay. Okay. So in the last 5 minutes, I want to make this imaginary DOZZ formula show up. And I'll do it at high level instead of at the level of details. So we had a story where we cut a disk by an outermost CLE loop around the origin. We get an annulus and a disk. Now we do the same thing, except that we pick 3 marked points on the sphere, and we cut along the 3 outermost CLE loops around the 3 points. So topologically, what you're going to get is one of these pair of pants regions. It's a cute name, but that's also the technical term in topology. So we call it the quantum pair of pants. It's unrelated to a quantum zipper, but that's a bad joke. Okay, so you get 3 network regions. And the claim is that you know the joint law of all 4 things. And this is again, or you can define the quantum pair of pants so that this identity holds. Okay, so this looks exactly the same as we had in the annular story. You've got quantum pair of pants ABC, quantum disk, quantum disk, quantum disk. And then we have this factor ABC, because for each disk you have a different number of ways of gluing it to the pair of pants. So this is a natural identity to write down. And then again, using the solvability of LKG and CLE together, you can write down the partition function for the pair of pants. So the pair of pants has 4 geometric observables: loop length 1, loop length 2, loop length 3, or boundary length, sorry, and the total area. And all 4 of these jointly you can write on the law, and it's encapsulated by this identity over here. Okay, the argument is essentially along the same lines as the quantum annulus. You use solvability of loop lengths of LKG and CLE, and then you do some Levy process computation to get this. Okay, so I want to write down a different 3-point function for CLE, and this one is related to the one we spoke about on Tuesday. So instead of counting the number of separating loops and taking some exponential of that and expected values, we'll instead look at the joint moment of the distances from the points 3i to the outermost loop eta I around the point. Okay, so in the figure we have 3 marked points on the sphere, namely this red, green, and blue point. And then we also draw these outermost loops. I color them in red, green, and blue. We look at the conformal radius of the loop viewed from the point. So you get 3 random variables which are correlated in some messy way. If you look at the joint moment of these 3 conformal radii, as usual, you get this kind of expression, which we've seen multiple times. The dependence on the locations is trivial. You get some unknown constant in front, which captures all the. This one is hard to compute. And the goal is to show that this unknown constant is secretly the imaginary DOZZ formula. Okay, so you just want to compute this joint moment of the conformal radii. The way you do it is the same story that we had for the quantum annulus. You start with the Liouville field with 3 gamma insertions. This corresponds to the 3-point quantum sphere. You cut by a CLE, or more specifically by the 3 CLE loops. This is going to give you 4 surfaces, 3 with the disk topology and 1 with the pair of pants topology. And this is what we get. So this is exactly analogous to what we did in the quantum annulus setting. So now we're going to do the same trick. We replace each of these gammas with alpha 1, alpha 2, and alpha 3 using this reweighting trick over here. So you reweight the law of the field near each of your 3 points by some quantity, send it to 0. And the new statement you get is, if you have a Liouville field with 3 different insertions, alpha 1, alpha 2, alpha 3, and you cut by CLE, but with some kind of weighting by the conformal radii of each of your 3 loops, you're still going to have this decomposition, but now again with the alpha I instead of gamma. So from the previous slide to this slide, we're just carrying out this computation we've already done in this modified setting. Okay. And now the point is that we can do the same idea where we compute the total mass of the left and right hand sides. These are measures and you can compute the masses and they should agree, but this doesn't work here because these are infinite measures. Right? We know that for the Liouville field, it's an infinite measure. So, because we don't have any fixed boundary length or fixed area or anything. So instead of computing the total measure of left and right-hand sides, we want to take a different observable. We want to integrate against this quantity, which is the e to the minus the LQG area of the surfaces. Okay, so on the left-hand side, well, the left-hand side factorized before into some CLE thing and some LQG thing. This quantity only depends on the LQG, and it becomes this this correlation function of Liouville theory on the left.
So this mu is 1, right?
Yeah, that's right. So here we set mu is the cosmological constant mu is equal to 1. Yeah. On the right-hand side, you have the CLE joint moment of your 3 conformal radii. And then, because quantum LQG area is additive over, so you just take e to the minus a for each of your 4 pieces. Okay, so you get this kind of messy, this kind of not too bad identity. And the point is that everything in this identity can be computed except for this one. So this is where we use the solvability of Liouville conformal field theory. This first expression is your DOZZ formula. The second expression over here, with the Liouville field on the disk, this is something like a structure constant for boundary Liouville, and this was solved. And this quantum pair of pairs we discussed a couple slides ago. This one is also explicitly known. So you get 3 different pieces which you know, and one that you don't, and so you can solve for this joint moment. Okay. You can see this is the last slide, but I have one comment about this. So if you remember, the imaginary DOZZ formula was kind of nasty in that it contains these double epsilon functions, and the DOZZ formula also contains the same double epsilon functions. What turns out to happen is that this combination on the right-hand side here contains 0 copies of the double epsilon function. So all the double epsilon functions from your DOZZ formula on your left end up going inside, giving you the double epsilon functions for your conformal radius moment. And yeah, so because this thing contains a bunch of double epsilons, this thing also does, so that they cancel out, so this product doesn't contain any of that. Okay. So that's how you get the imaginary DOZZ formula to show up. You get the double epsilons from this, and they become the imaginary DOZZ when you evaluate this thing. Okay, I think that's the end of my lecture. Thank you very much for your attention.